Yeah, we go on with the mathematics of artificial intelligence as we consider how AI learns from mistakes. On every AI tool you have, especially generative AI, you always have that remark that AI can make mistakes. But the beautiful thing is that AI can make mistakes, but it can learn from mistakes and get better and better. So let's look at this. So our objectives here will be to explain how AI learns through repeated mistakes, understand the intuition behind optimization, define error and loss functions, explain how machine learning minimizes error, understand gradient descent intuitively. Interestingly, I think in the next video we'll be looking at gradient descent, on its own as a separate video dedicated to it. Although we've been seeing it uh, elsewhere, and we are looking at it here too. But then there's a whole video dedicated to it very soon. So implement simple optimization examples in Python and describe how AI training systems work. Then you identify real-world applications of AI training. So let's go ahead to the introduction. Imagine we know that humans learn by making mistakes. For example, when learning to play basketball, so if you fire your first shot and you miss, you then adjust your aim and you try again. Well, maybe you miss the next time, but the miss will not be as bad as the first miss, right? And then you continue practicing and you eventually become accurate. That's how the best of basketballers are made, right? So artificial intelligence learns in a remarkably similar way. Instead of feeling disappointed by mistakes, AI measures every mistake mathematically and adjusts itself to reduce future errors. So we have the learning cycle as follows. We have prediction, then the prediction is then compared with actual answer, and then the error is calculated, parameters are adjusted, prediction is made again, and this is repeated thousands of times until the right result is obtained. So this repeated improvement process is called optimization. So optimization is you want to get the best results possible with whatever you have. So we move on to talk about the basic learning cycle. So every machine learning algorithm follows the same general process. You input data, even if it is generative AI, you put your prompt. That's like the input in that case. So input data, then the model makes prediction, and then you compare prediction with actual value, and then you calculate the error, you update the parameters, rinse and repeat until you get the result you desire. For instance, you have an example here. Suppose the actual house price is $500,000, but then AI predicts $420,000. The prediction error is 500,000 minus 420,000, which is 80,000. And then the model now asks, how should I change my parameters so that the next prediction is closer to the correct answer? So that next time we'll get something closer than 420, closer to 500,000 and 420,000. So optimization answers this question. So well, it is the process by the process of optimization. By now, you already see that it is by the process of optimization that AI learns from mistakes. So the question is, what is optimization? It is the process of finding the best values for a model's parameters so that prediction errors become as small as possible. So imagine adjusting the volume of a speaker. It can be too low, it can be too high, it can be just right. And then optimization is simply searching for that best setting that is just right. So in machine learning, these settings are called parameters. So the various parameters determining whatever you're measuring. So the most common parameters are the weights and biases. So if you remember the equation, which is say y equals wx plus b. So w is the weight, b is the bias. So those are the most common parameters. So if you represent them in matrix form, you can then have several of those weights and several of those biases. So training gradually adjusts these numbers until the model performs well enough. So imagine this example. Okay, if I talked about this y equals wx plus b, right? Consider the simple linear model y equals wx plus b, where x is the input, w is the weight. So the weight determines how fast, things happen. Like it's more like the slope. And then b is the bias, maybe some error, some baseline value, so to speak. And then y is the prediction you're trying to make. Initially, the model may choose random values such as w is 0.5 and b is equal to 2. And these values would usually be poor. The initial values would usually be poor, but they are starting points for the prediction for the optimization process. So after repeated training, they gradually improve. And then imagine when you have this example, training stage and weight. So at the initial stage, the weight is 0.4. After 100 updates, it can then come to 1.20. After 500 updates, it can come to 1.85. You see, it's increasing towards a value. And then after some several steps, it can then become like 2.00. So it converges to that best weight possible. So the model slowly discovers parameter values that minimize prediction error. That is what is happening there. And the question again is, what is error? Of course, it's obvious what error is, right? It is basically the difference between the actual value and the predicted value. So error measures how far a prediction is from the correct answer. And the simplest definition is error is equal to actual minus prediction. Example, actual value is 100, prediction is 90, error is 100 minus 90, which is 10. So a smaller error indicates a better prediction. So the better and better this prediction gets, let's say the prediction goes to 95, then the error is smaller and it becomes 5. If the prediction goes to 99, the error becomes 1 because the prediction is better now. So, and then that takes us to the idea of loss functions, which I think the last video or so was about loss functions. So machine learning rarely uses raw error directly, right? So instead of just computing the error the way we computed it up here by just subtracting, it is a bit more nuanced than this in machine learning. So machine learning rarely uses raw error directly. Instead, it uses a loss function. So a loss function converts prediction errors into a single numerical value that represents how well the model performs. So common loss functions include things like mean squared error, MSE, mean absolute error, MAE, cross entropy loss, hinge loss, log loss. The objective of training is always to minimize whatever loss you might have in your system, in your in the process. So let's take the errors one after the other. Talk about mean squared error. I mean, as the name implies, the most common loss function for regression problems is the mean squared error. So here you have a mean, and that's why in the formula you have 1 over n. That's like the idea of mean. Squared error, that's the square of the errors. So it is defined as MSC, which is mean squared error, is equal to 1 over n, summation from I equals 1 to n of yi minus yi cap all squared. So mean squared error, right? So you take, you have a prediction, right? So you have a set of predictions, so to speak. So these are the set of predictions, yi. So you take the difference between each prediction and the actual value, and the actual, okay, you have the actual value minus the prediction, right? So you take the difference between those two. So the differences are now squared. And then this summation tells you that all those the differences are squared. Then all those squares are now added together and divided by the number of items you have. So that is why it's called mean squared error, the mean of the squared error. So the error is the difference between the actual value and the predicted value. Then the square, you square that, then you sum it all up, then you get, and you divide by n, and you have the mean squared error. So yi is the actual value, yi cap is the predicted value, n is the number of observations. So you divide by the number of observations, then it becomes the mean squared error. So now, why square the errors? That's the question you might be thinking about. Suppose the errors are 5 and minus 5, for instance. Adding them gives 5 plus minus 5, which is 0. Okay, in that case, it looks like there's no error, whereas there are errors like that, and there are significant errors, by the way. So this incorrectly suggests perfect predictions. So what mean squared error then does is when you square now, each 5 gives you 5 squared. So 5 squared is 25 and minus 5 squared is also 25. Now every mistake contributes positively to the total error. So every mistake is a departure from the actual result. So 5 is equally far away from the actual value as minus 5. So but by just adding up, it looks like there's no error at all, but then you get a clear picture, the true picture when you square the errors. So using mean squared error now, you have 25 plus 25, that's 50, and then you divide by 2, and then the mean squared error is 25, as compared to 0, which you would have got when if you added directly. Now every mistake contributes positively to the total error. That's what we see there. Now let's look at computing mean squared error. Suppose the actual values in a case are 10, 20, and 30, and the predictions are 8, 18, and 20. The errors are 10 minus 8, 2, 20 minus 18, 2, 30 minus 40 minus 10. The squared errors are 2 squared is 4, 2 squared is 4, minus 10 squared is 100. The average of that would now be the mean squared error. The mean squared error is then 4 plus 4 plus 100 all over 3. That's 108 over 3, which is 36. Therefore, the mean squared error is 36 in this case. So the mean squared error for this set of values and the predictions attached is 36. Now, and we can use a simple Python code to take care of that. So import number as NP. Then the actual values are 10, 20, and 30. The predicted ones are 8, 18, and 40. Then the mean squared error will be the mean. Of course, mean is coming from NumPy. Mean of actual minus predicted raised to power 2. And then if you compute that, you get this, that is 6.0 you have right there, which of course tallies with what we had. Of course, this is just you just have three values here, so it's easy to just do it manually. But when when you have like 3 million values, then programming becomes the real deal. Now, let's look at optimization intuition here. So we've seen that optimization is the process of reducing the error to the barest minimum. So imagine walking down a mountain while blindfolded. That's a very dicey thing to do. You cannot see the valley. You can only determine whether each step moves you uphill or downhill. So you're blindfolded on a mountain. So if you take a step, of course, you can feel it in your body that, oh, if I take this next step, I'm going up or going down because you're blindfolded, right? So you can only determine whether each step moves you uphill or downhill. So if every step moves downhill, you will eventually reach the lowest point. So the idea is that you keep, if you want to go down, if your aim is to go downhill, you want to be sure that every step takes you downhill. If you want to go uphill, you want to be sure every step takes you uphill. But if one step goes downhill, the other goes uphill, so there can be that's a kind of system that is not converging. So optimization works in exactly the same way that if your aim is to go downhill, every step eventually takes you there. So the model repeatedly adjusts its parameters so that the loss becomes smaller and smaller. Imagine starting out from this point and you keep taking a step until you get to the barest minimum. So you have the parameters here and you have the losses increasing. I mean, the losses decreasing downwards this way. So like that. So the bottom of the curve represents the minimum loss now. So the bottom of the curve is where you have the minimum loss, somewhere around here. Now, we also have the cost surface, right? For models with many parameters, the loss function becomes a multi-dimensional surface called the cost surface because it's not just a minimum point, it's more like a surface. So with many parameters, you have a surface where you have the minimum value. So the height represents the loss. Training attempts to move from higher regions toward the lowest point on the surface. So you have to move somewhere down the surface. Now, let's talk about gradient descent, which we've talked about before, and we're still going to talk about again because it's about the most important algorithm as far as loss is concerned. So the most widely used optimization algorithm is gradient descent. Its steps are compute the current loss, measure the slope or what you call the gradient, move in the opposite direction of the slope. That's why you have this negative sign. Then you repeat. As you keep doing that, you get where you're going at some point. So the update equation is simply theta new equals theta old minus alpha uh, gradient of j of theta, where theta represents the model parameters, then alpha is the learning rate, the gradient of j of theta is the gradient of the loss function. So gradient descent repeatedly moves downhill until the loss becomes as small as possible because we want to minimize loss. We don't want it to be too big. So, and we have the learning rate here, which is alpha. So it is a very crucial parameter there. So the learning rate controls how large each optimization step should be. So learning rate is more like as you're walking downhill, right? How wide of a step do you take? So if you take, of course, on a rock, you have to be careful, right? So if you take small steps, you get to the minimum value longer than when you take bigger steps. But if you take bigger steps, you can easily get into trouble because you are blindfolded on a mountain. So you have to find a balance between how the kind of step you should take and how fast you get to your results. So the learning rate controls how large each optimization step should be. So small learning rate means slow learning. So you are moving slowly, and then it is also stable so that you don't tumble off the mountain. Then large learning rates, of course, that guarantees faster movement. But the problem is you may overshoot the minimum. So you may take steps that will go beyond the minimum, and then it can become unstable. I mean, you can fall off the mountain if you take too large steps that are too large. Then typical values of learning rates are something like 0.1, 0.01, 0.001. So you need to choose an appropriate learning rate. It is an important that because that is important part of model training. So of course, most of the times you may have to try different ones to see which one gives you the best result. Imagine that we have x to be 8. That's the initial parameter. Learning rate is 0.1. So for step in range 20, so in 20 steps now, you now have a gradient 2x. So the new value now, x new is now x old minus learning rate multiplied by the gradient, which is 2. Of course, we already have x here. So if you do that now, that if you run that, you get so here the range 20 means you're starting from 1 to 20. So or more like 0 to 19. But then the steps start from 0 to 19, and that's like 1 to 20 here. So in step 1 now, so that's more like saying 8 minus 0.1 times 2 times 8. So that's 8 minus 0.1 times 16. So that's 8 minus 1.6, and that simply gives 6.4. And then the next one now, you have 6.4 minus 0.1 times 6.4. It gives you 5.12. And the next one is then 5.12 minus 0.1 times 5.12. You get 4.09600. And it keeps going like that until you get to the 20th step. And you can keep going. Now, let's see what happens here. Let me try something. Let me make it this 200 and see how far so at a point, okay, in fact, we don't have to go to 200 even before we get the result we want. Uh, so the decimal following, if you are going by 6 decimal places, the result already converges to the minimum around steps. Okay, step 62 still has some values. Maybe around step 75, you already get the best result. So other steps may not be necessary. So that's the kind of thing. So the deal is, as it keeps going, it tends to converge towards a particular value, towards a minimum value. Of course, we know that for the gradient to be 2x, it means this is coming from x squared. I know the minimum value for x squared, which is the parabola, is at 0. That kind of thing. So we have that. So that's how that works until you get to the minimum point. Now, we have that. So you can also you may want to visualize that, right? Like I said the other time, a gradient of 2x could only have come from x squared. So you may want to visualize that. Maybe here you want 4 points. Okay, let's see. You have, yeah, from -5 to 5, that's you define x on that range, and then you plot the graph like this. So, and then if you run this, it shows you the gradient descent on y equals x squared. It starts from somewhere. It's just like what we had before. It keeps going all the way down to 0, like we had up there. The first value we got was 6.40 something. So like that. So we then come on to the idea of error minimization in machine learning. Consider the linear model y equals wx plus b. So suppose the training data are x and y, 1, 3, 2, 5, 3, 7, 4, 9. The correct relationship is y equals 2x plus 1. So you see that for every y is equal to 2 times x plus 1. So 3 is 2 times 1 plus 1. That's 3. 2 times 2 plus 1, 5. 3 times 2, 6 plus 1, 7. 4 times 2, 8 plus 1, 9. That's why. So this is the relationship between the data. So initially, the model may use w equals 0 or b equals 0, which produces poor predictions if you start with these initial values. But each optimization steps adjust w and b. And eventually, you end up getting w that is roughly like 2 and b that is roughly like 1. So the prediction error becomes very small in that case. So here now we have that kind of idea. So putting those two data together and having the initial value here, and then we have to fix a learning rate of like 0.05. So if you run this now, you get the final weight now becomes like 2.0 and bias is 1.0, like this. So no matter what the learning rate you choose, the only thing is that the number of steps you may need to get there may not be small, but you end up getting roughly the same thing. So with 0.01 now, you need to do more than 500 steps to get the same result you would have got with 0.05. So 0.05 gets there faster than 0.01. But you can see the value was for weight was close to 2.0 and bias was also close to 1.0. So we then go on to talk about training systems. A training system is the complete process used to improve an AI model. So the complete process that you use to improve an AI model is the training system. So the workflow consists of, collecting data. After collecting the data, you prepare the data, then you initialize the model, you forward pass, you compute the loss, you compute the gradients, you update parameters, and you repeat, you validate, you test, and deploy. So the major stages are then the following: data collection, data preprocessing, model initialization, forward propagation, loss computation, back propagation, parameter optimization, validation testing, and deployment. So some of these concepts like back propagation, we are still going to talk about it in a future video. So let's talk about applications of AI training systems now. So training systems are used in many real-world applications. So like in image recognition, like for face recognition, medical image analysis, object detection. In speech recognition, you have to you apply training systems with voice assistant, automatic transcription, and speech to text systems. Then you have natural language processing. You have machine translation, chatbots, text summarization, large language models. Then you have recommendation systems like Netflix, Amazon, Spotify, and YouTube. So what makes you see some videos recommended to you? So over time, as you begin to, when you go to YouTube for the first time, you see everywhere is blank. You have no history. But by the time you watch one or two videos, the system learns your pattern, the kind of things you watch, and it begins to recommend for you things that are related to that. Those are recommendation systems. So it happens like on Netflix, Amazon, Spotify, and YouTube, like that. Then autonomous vehicles for lane detection, traffic sign recognition, and obstacle avoidance. And in healthcare for things like disease diagnosis, tumor detection, and drug discovery. So then we see some common optimization algorithms. We have the batch gradient descent, which uses all data for each update. It is stable, but it can be quite slow because it is using all data. Then stochastic gradient descent, it uses one sample at a time. This can be fast but noisy. Of course, that is stuff of stochasticity, right? Then you have mini batch gradient descent, which uses small batches and it is efficient and widely used. Then you have momentum. It adds previous updates and that leads to faster convergence. So it's more like what any updates you get now, you hold it and you add the next one to it and you upgrade and till you get the result. So that's why it converges faster than the ones we've seen. Then you have RMS prop, which is adaptive learning rates, which is good for complex problems. And then you have the Adam optimizer, which combines momentum and RMS prop. So it combines these two, and it is the popular default optimizer like that because it's a combination of momentum and RMS prop. Now, in summary, artificial intelligence systems artificial intelligence learns by repeatedly improving its predictions. The complete learning cycle is make a prediction, compare it with the correct answer, compute the loss, calculate gradients, update model parameters, repeat until the loss becomes sufficiently small. Then we see that optimization is the mathematical process that enables AI to learn from mistakes. So optimization enables AI to learn from mistakes by uh, minimizing over and over again the loss function until we get to the BRS minimum. So error minimization provides the objective, while optimization algorithms such as gradient descent provide the mechanism for achieving the objective. So you want to minimize error, then use gradient descent to achieve that. Then modern AI systems, from image recognition to large language models, depend on this continuous cycle of prediction, error measurement, and parameter adjustment. So, as usual, we have our practice problems. So here you can see problems 1 to 4 clearly. And of course, I get to solve two. Here I'll be solving problems 9 and 18. Problems 9 and 18. So you can see 1 to 4 here. Then we have 5 to 9 here. So I'll be solving 9. Suppose the parameter update rule is theta new equals theta old minus alpha, the learning rate, multiplied by the gradient of j of theta. If theta old is 5, alpha is 0.2, gradient of j of theta is 3. Compute the updated parameter. So you're going to solve that. Then you have 10 to you can see 10 to 15 here, clearly 10 to 15. Then Okay, let me flash 10 to 15 again. 10 to 15. Then 16 to 20. Okay. Yeah, you can see all of 16 to 20 now. Okay, so I'll be solving 18 also. A model initially has a loss of 50. After several training epochs, the loss becomes 8. Calculate the percentage reduction in loss. So we'll be talking about that too as we bring this to a close. So let's go for problem 9 to start with. Problem 9. So we see that the parameter update for gradient descent is theta new equals theta old minus alpha grad j of theta. And then we are given some values, given theta old to be 5, alpha to be 0.2, and the gradient of j of theta is 3. So the next thing is to substitute. So we substitute these values into the update equation, So we then have theta new to be theta old, which is 5, minus learning rate 0.2 multiplied by gradient, which is 3. All we got from here. So theta old is 5, alpha is 0.2, and the gradient is 3. So that means that theta new is equal to 5 minus 0.2 times 3 is 0.6. So theta new then is 4.4. And that's how that goes. So if you care for interpretation, so the parameter, you see the parameter moved from 5.0 to 4.4 in the direction that reduces the loss. Okay, this single update this single update is one step. That is one step of the optimization process. Is one step of the optimization process. So, or you can call it one iteration. So repeating many such updates, gradually moves the model toward the minimum of the loss function. Okay, so we go on to problem 18, having taken care of 9. So let's talk about problem 18. Okay, you remember the initial loss was 50, the final loss was 8. We now need to calculate the percentage reduction. So there we see initially the model has a loss of 50. Then after several training epochs, the loss decreases to 8. Okay, so what do we do? Okay, we are asked, right? We are asked to calculate the percentage reduction in loss. Okay, so we do step one. Step one, we find the reduction in loss. Find the reduction in loss. So reduction is simply reduction is equal to 50 minus 8, and that is 42. That's step one there. Step two, divide by the initial loss. Divide by the initial loss. So we have 42 over 50, which is 0.84. Then we finalize with step three. In step three now, so it converts to a percentage. Convert to a percentage. Convert to a percentage by multiplying by 100. So that's 0.84 times 100. That is 84%. So that's what we have there. So we can say, therefore, percentage reduction is equal to 84%. So the interpretation then, the model reduced its loss by 84% during training. So this indicates that the model's predictions improved substantially over time. However, a large reduction in training loss does not automatically guarantee excellent performance on unseen data. The model should also be evaluated on validation and data sets. Validation and test data sets to ensure that it has learned general patterns rather than simply memorizing the training data. So that's what we have as far as that is concerned. So we are done with this video now, how AI learns from mistakes. So I'm going to show the problems once again as we end this. So you see problems 1 to 5 here, or even, yeah, you can see problems 1 to 6, 1 to 6 here, then 7 to 12, or even 7 to 13, and 7 to 13, then 14 to 18, the rest. Yeah, so that's that. Let me know how helpful this is for you. And if there's something else you'd like me to do, feel free to let me know. If you have subscribed to this channel already, thank you very much for doing that. And if you have not subscribed, why not go ahead and do that right away? Um, so you just subscribe and hit on the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges you find out as you click on join. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.